how long does it take to boil a kettle of water? Well, I have 1,000 millilitres of water. The density of water is about a gram per centimetre cube. So if I have 1,000 centimetre cubes of water, that is approximately a mass of 1 kilogram. To bring water from room temperature, 20 degrees Celsius, to boiling point, we need to raise its temperature by 80 degrees. And I have a kettle here, on the bottom of which is a label which indicates its approximate power output. And that is 2,800 watts. The specific heat capacity of water is 4,200 joules per kilogram per degree C. Let's assume energy is conserved. That's a law of physics. We can say that the power of the kettle multiplied by the time it's on for, the time it takes to boil the water, is going to be equal to the thermal energy delivered to the water, which, if you've done GCSE physics or chemistry, you'll be familiar that that is given by the mass times the specific capacity times the change in temperature. However, there'll be some energy losses to the surroundings. The kettle isn't perfectly insulated. So, looking at rough efficiency of a kettle, they're pretty good, between 80 and 90%. We actually need to add a factor here because only, let's say, 85% of the energy the kettle delivers via the filament will actually contribute to the water heating up. Some will be lost to the surroundings. We're going to do a very rough calculation to predict how long the kettle will take to boil. Let me put my kilogram of water at 20 degrees into the kettle. What I'm then going to do, and you can hopefully see that the kettle will come on, I'm going to start my stopwatch and turn the kettle on at the same time. There we go. Right, let's work out how long this should take. Well, if I put my numbers in, I have 0.85 times by the power of the kettle, which is the energy delivered per second, multiplied by the time taken, that's what we want to find. The mass of water is 1 kilogram. The specific heat capacity of the water is 4,200 joules per kilogram per degree C, and delta theta is the final temperature minus the initial temperature, which in this case is going to be about 80 degrees. So what I'm going to do is I'm going to rearrange this. So you might want to pause the video and work this out yourself, but let me rearrange this. So we'll have a 0.85 times by the 2,800 on the bottom. Like any good scientist, I have my calculator at the ready. Although, do you need a calculator? Always better to be safe than sorry, particularly when you're filming a video like this. 141 seconds. Now, 141 seconds, let's say 140 as a suitable level of precision, just because a lot of these values are approximate. I've not really thought about how accurate they are. This is about 2 minutes and 20 seconds. So we're looking for somewhere about 2 minutes 20 seconds for the water to start boiling. How close do you think I'm going to be? After all, I've not spent an awful lot of time justifying the values that I've given. So, you ready? Here's the kettle. Now, I think you'll agree that has started to boil, so I'm going to stop the stopwatch now. 2:11:07. 2 minutes 11 seconds. 2 minutes 20 seconds. I would say that is not bad for an approximate calculation. Don't you love it when science works?